Well, hello again. In this example, you will use the double integration method to find equations of deflection for a beam. We're going to look at this particular beam, noting a couple of things before we get started, is that segment 1, that's segment AB, is defined by this coordinate system, whereas segment BC is defined by this coordinate system going in the opposite direction. We've already taken the liberty to define the moment equations that describe each of these segments. So the next thing we're going to have to do is get the equations of boundary conditions, equations that describe the boundary conditions. So I'm going to just write that here, the BCs, and we do that by first sketching the deflected shape. These don't have to be perfect, but just to give you an idea of what it looks like. We will then point out places where we already know the displacement. This is based upon our support conditions. We know that the displacement here is equal to 0, and we also know that on either side of point B, that theta is the same. In other words, the rotations on either side are the same. Now that one's going to run into a little bit of a snag that we'll point out here in just a minute, simply because the coordinate systems that we're dealing with are going in opposite directions. Here's going that direction, this is going in that direction. But it'll be easy enough to deal with. Let's take care of segment AB first. We know that the displacement at point A, and this is how we describe point A, we know that that is 0. We know that the displacement at point B is also 0, so point B is described by this as 3L over 4. Now let's look at segment number 2. We know that the displacement at point B is 0, and this is the way we're going to describe that. That's where x2 is equal to L over 4. We know that's 0. And then we know that the rotations on either side of point B are going to be the same. So let's describe point B here again. That's at x1 equals 3L over 4. And we know that that rotation has got to be the same as for segment 2. Let's describe point B there. That's at x2 equals L over 4. But because of the separate coordinate system, we know that that relationship has got to include the negative. So the next thing we want to do is go ahead and take our moment equations and get those integrated. So for segment number 1, we get the theta equation by integrating m1 over ei relative to x1. That will give us this 1 over ei negative WL x1 squared over 48 plus c1. And for y1, we then integrate theta 1 with respect to x1. Now to give us 1 over ei negative WL x1 cubed over 144 plus c1 x1 plus c2. Now please notice that in both integrations we had to get integration constants that were present there. So that handles segment number 1. Let's go ahead and get segment number 2. Theta 2 is equal to the integral of the moment in segment 2 divided by ei relative to x2. This will give us 1 over ei negative wx2 cubed over 6 plus c3. Now don't make the mistake many do, and that is start calling that c1. We are going to have 4 unique integration constants, so don't give them the same labels. We've got y2 is then the integration of theta 2 with respect to x2. That will give us 1 over ei negative w x2 to the 4th over 24 plus c3 x2 plus c4. So those are actually the full equations for deflection, and so the only thing we really need to do at this point is to solve for what those constants are, and we will do that using the boundary conditions. So here's boundary condition number 1. We've written this before. Y at x1 equals 0 is equal to 0. So let's go ahead and take that expression for the first segment. So that says 1 over EI is equal to negative WL times 0 cubed over 144 plus C1 times 0 plus C2. All we are doing is we are substituting in wherever there's an x1, substituting in my known value right here, and we then set that all equal to the known value of deflection. And when one does that, we will find out that in this case C2 is equal to 0. Once we do that, we are ready to move on to boundary condition number 2. And that boundary condition states this, that y, the displacement when x1 is equal to 3L over 4, it is 0. So let's take our same deflection equation, 1 over EI, negative WL, and anywhere that an x1 appears in the equation, plug in your known value, which is 3L over 4. That is cubed, divided by 144 plus C1 times 3L over 4, and that is equal to 0, and we can then come back and solve for C1 is equal to WL cubed over 256. Okay, so we have used the first two boundary conditions and found the first two constants. Let's move on to another boundary condition here. So boundary condition number 3. The order of this doesn't ultimately matter too much, but I'm going to go ahead and use the rotations here. And the boundary condition that we decided on was theta of x1 is equal to 3L over 4 is equal to the negative theta of x2 equals to L over 4. So we can go ahead and plug that into our rotation equations. So negative WL 3L over 4 squared, all divided by 48, plus WL cubed over 256. You'll notice that's that C1 value that I've found out previously. And that is equal to the negative of negative W. And this is where we plug in the L over 4. And that will be cubed, all divided by 6, plus C3. And one thing you're going to notice is in this particular equation I've left off the 1 over EI. It actually didn't become necessary for me to have that there because in the end those will cancel out. But it's probably more proper to include that when you write those out. Well, you'll notice that C3 is the only unknown in that equation, so we can do a little bit of algebra and find out that C3 is WL cubed over 96. Then we are ready for boundary condition number 4, which states that y at x2 is equal to L over 4, that the displacement there is 0. So we'll go ahead and get that in here. Negative W times L over 4 raised to the 4th power, all divided by 24, plus WL cubed times L over 4 over 96 plus C4, and all that is equal to 0, and thus C4 is equal to negative 15 WL to the 4th over 6,144. I will tell you that many people struggle with the algebra on this, not so much that they don't know what to do, but rather just because you can kind of get lost in it. One thing that I have noted in the past that happens quite often is that when working out the algebra may come up with this term and this term having different sets of units. What I mean by units is just take a look here. This one has units of WL to the 4th. if you came up with one that was WL cubed and the other one was WL to the fourth, you know that you've messed the algebra up somewhere because you have to have consistent units. To finish this up, we will simply plug the constants into our equations, and with a little bit of algebra and collecting like terms, we come up with these two sets of equations. Now, I never like these equations being reported unless you have an appropriate domain with those. And so it is the same domain that was given for the moment equation. So 0 to 3L over 4, and this one has the domain of 0 to L over 4. That completes this example. As always, it's a beautiful day to study structure.